The last member of this panel is Paul Lemieux, who is with the EPA Office of Research and Development, their National Homeland Security Research Center, the Decontamination and Consequence Management Division. Welcome.
Thank you, Dr. Goldman. I'm honored to be here. I'm primarily going to be talking about treatment of waste, but this is a big integrated incident that involves many different considerations that impact other considerations, like how they approach the infection control affects how the waste is generated. What disinfectants you use affects how the waste is generated. So everything affects everything else in this situation, and we need to be able to be thinking about all of them at the same time. When people talk about waste management, there's a number of steps of waste management, some of which can result in potential exposure to the waste management workers. And there's technical issues associated with some of them as well. I'm going to focus on the treatment aspect of it, but people need to remember that there's people that package this stuff up. There's truck drivers that transport it. When it arrives at the treatment facility, they may have to open up the packages. DOT has fairly stringent requirements for how to package Category A bioagents, and that impacts how the treatment facilities can operate. And then you have to transport them to your ultimate disposal facility, of which it's been mentioned that there's a stigma attached with some of this waste, that it's not a technical issue, but the waste management facilities like the landfills, they're typically publicly held companies. And you know how the stock market can fluctuate based on unreasonable assumptions, and so they have it may not be technically founded, but they do have a legitimate concern about their business assets and their stock price. When we talk about the waste streams we're going to be dealing with, you got the personal effects of the people, the conventional medical waste, non-porous materials typically, but in this situation we're likely to have a lot of porous materials. So like linens, scrubs, pillows, mattresses, especially if you have to clean up a contaminated residence or public spaces, buses, other transportation vehicles. There's decontamination residues associated with cleaning up the premises and the hospitals and the vehicles. They may not be contaminated because they have disinfectant in them, but they may be considered to be RCRA hazardous waste depending on what the characteristics of them. You have decontamination residues from cleaning up personnel and pets, PPE, potentially a lot of wastewater and rinsate that you might have to deal with. The limited information we have now suggests that these patients generate about 30 to 40 times the amount of medical waste that normal patients generate. So we're looking at maybe 15 like 35-gallon drums packed in 55-gallon drums packed in 95-gallon drums. And that's a lot of material that has to be hauled around. It has a lot of potential for worker exposure if you have to open it up, because only a limited number of disposal facilities or treatment facilities can actually accept this stuff into them. And it's very expensive to manage. When you talk about management of waste, there's all sorts of different aspects that simultaneously have to be considered. How appropriate is a facility? Is the facility available? Does it have sufficient capacity? There's other issues related to public acceptance. A lot of the waste management facilities have worked very hard to develop a rapport with their respective communities, and they don't want to have to jeopardize that by accepting waste with a potential stigma attached to it. Sampling and analytical methods. A lot of states may require you to assure that the waste doesn't have any residual Ebola in order to send it off to a landfill. And it's a major data gap of how to analyze material like waste and verify that there isn't any of your agent in it. Waste treatment, it has a lot of analogies to disinfection. This is an example of the Spalding scale, where typically the bacterial spores are the most difficult to disinfect, and viruses are much more easy to disinfect. That's kind of in general, though. The matrix they're on can impact the ability to disinfect them. If they're bound up in a porous material, the porous material may react with the disinfectant, resulting in you may need to hit it longer or hit it with a more concentrated solution. Well, thermal inactivation, which is the way that we deal with the waste, it's analogous to disinfection. So the spores are much more difficult to thermally treat, and the viruses are much easier, but there's considerations related to the matrix they're bound on. We've done a lot of work in the past looking at waste treatment for a Bacillus anthracis incident. So we've been testing with the spore-based organisms, and the organisms of concern are more easy to destroy. When we look at what are the options we have, pretty much we have incineration and autoclaving. Incineration, the Dallas materials got sent to a hazardous waste incinerator, and they were able to accept the barrels of waste and feed it directly into the incinerator. So they were not subjecting the workers to any additional potential exposure. They can accept large items. They may not be allowed to accept biological waste, though. They may have to get a permit modification, or maybe the state won't let them at all. You have medical pathological waste incinerators. Even the large ones, though, aren't set up to take barrels. They take boxes and bags, so they may have problems fitting some of these large items in. If you send a mattress off, you're limiting yourself to where you can send it. Again, there's worker health and safety concerns there. The other option is autoclaving. Some hospitals have on-site autoclaves or on-site incinerators, but it's only a small fraction of them now that have that. So they're centrally located medical waste autoclaves that you send materials to. They can take some large items. They're pretty large. They're about the size of a gasoline tanker truck. So they can take some large items. You may have to slightly adjust the operational conditions, though, in order to make sure that you can successfully autoclave some of the more difficult items. And again, there's worker health and safety concerns. Incineration, we're talking high temperature combustion, typically around 1,000 C. And a lot of these incinerators have two chambers, where the first chamber processes the solid waste, kills the microorganisms, releases combustion products into the gas, and generates fly ash. And then it all goes into a secondary chamber, which successfully destroys any of the toxic combustion byproducts and any microorganisms that got out of the primary chamber. Then they all have pollution control devices to catch the particulate matter and the acid gases, as well as prevent the formation of dioxins and furans, which they're of concern both from a permitting standpoint and a public health standpoint. And a lot of incinerators have very tight regulations on the dioxins and furans, and I'll get to why that's important in a minute. We've been doing some work looking at different aspects of incineration over the years. Back in the early 90s, the EPA was trying to figure out how they're going to regulate medical waste incinerators, and one of the ideas that they had was to do some testing where they feed large quantities of a non-pathogenic organism into the incinerator and then measure how much comes out in order to establish some sort of operating regime. They ended up abandoning that because it's extremely expensive to have to use enough of these surrogate materials, like hundreds of thousands of dollars just to get enough material that you can feed it in the hopes of being able to get something over your detection limit at the outlet. So we looked at those data and tried to do a statistical analysis to see what are the important parameters. We've also done some tests at our facility in Research Triangle Park, North Carolina, to look at incineration situations with porous building materials, because that seems to be one of the big knowledge gaps. So we did ceiling tile in particular are particularly pernicious. You could probably tile the space shuttle with ceiling tile. It's very heat resistant, it's very porous, and wet ceiling tile, we were pulling live spores out of the incinerator after 35 minutes at 1,000 degrees C, because it takes so long for the heat to transfer into some of these materials and boil off the water before you start heating it up properly. We also did some work looking at what is the impact of using like bleach disinfectants on some of these materials to see if the combustor emissions change from using those materials. Here's in brief the results from our test. We found that pretty much if you can get the material up to about 350 C, we were able to successfully kill the spores. So that means you have to leave things in long enough. Potentially you don't want to wrap them up too tightly when you send them in so that they aren't insulating the inner parts of the solid mass. But you can pretty much kill all of the microorganisms if you get the material hot enough. We also found that, at least in the pilot scale test, that there is the potential for increasing the dioxin emissions if you use large quantities of bleach and they're present in the incinerator feed. So the facilities would need to be cognizant of that. Some of the other implications is that it looks like maintaining the primary combustion chamber temperature and the secondary combustion chamber residence time were the two parameters that most assured the destruction of the microorganisms. The ash is not likely to have any microorganisms, but must be characterized in order to determine the disposal pathways, because they have to look for things like metals and leachability to make sure that they can send it off to a given landfill. And packaging is extremely important because this is all heat transfer limited. You want to make sure that the materials you feed in are not inhibited from being heated up by the process, especially if they're wet, because you have to get them up to the boiling point of water and drive the water off before they start heating up again. The second option is autoclaves. We're looking at a large pressure chamber where they put the material in, close it up, pull about 10 pounds of vacuum on it, then they pressurize it with steam up to maybe 30 or 40 pounds per square inch of steam. They hold it for maybe 45 minutes or an hour, and then they vent it. They try to maintain about 250 Fahrenheit for at least 15 minutes. It effectively kills the microorganisms. There's been an extensive history of using these things for non-porous materials. And then typically you then take the residuals and they either go to an incinerator or they may go to a landfill depending on what the state permitting requirements are. We did some tests about 9 years ago at a commercial autoclave up in New York State. It was a 96-ton-a-day autoclave. And we were focusing on the porous items. We used wallboard, ceiling tiles, carpet, and a sofa. And we embedded thermocouples and biological indicator strips, which is the normal performance test they use for autoclaves to assure they're operating correctly. And we embedded them into these materials, some of them on the outside, some of them on the inside. And then we varied the time and temperature and packing density in the autoclave to see if we were able to successfully kill the bugs. When we started doing these tests, we saw some strange results on the thermocouples during the first run, where it looked like all of the signals were converging on a single point. So we did some additional tests to look at the effect of multiple cycles, and that ended up being a fairly profound observation that you normally don't see when you're out on a field test. Usually you got to wait till you get home and analyze the data before you see anything really interesting. But what we found was that rather than going for a longer autoclave cycle where we were still not able to get all of the material up to the temperature of the autoclave, you can see this black line at the top was our control, which was essentially the freeboard temperature in the autoclave. The rest of them were all the thermocouples bound in wallboard. And running a double-length autoclave cycle, we still had maybe a third of our thermocouples were not even close to being up to the autoclave temperature. What we found, though, is when you run the second autoclave cycle, after you release the pressure from the first autoclave cycle and run it through the evacuation step again, you essentially pull all of the water out of the pores of these materials, so then when you hit it with the steam the second time, they're hot already and you don't get all this water condensing in the pores, and it brought all of the temperature readings right up to the autoclave temperature within a couple minutes. And this was borne out with the biological indicator strips, in that if we did this, we killed all of the BI strips, whereas in the one above, we did not. So we found that the second cycle is much more effective than running a longer cycle. We also found that cutting the bags prior to autoclaving improves the penetration, and separating the items improves the steam penetration. So there's limited capacity. The incinerators should use appropriate conditions to make sure that they operate properly. And there's some potential improvements could improve health and safety concerns for workers. Finally, just some of the data gaps. Trying to identify how we can operate the autoclaves when we're using the DOT recommended packaging. There's some testing being planned by New York State DEC to try to look at some of these issues. We need a good surrogate. You can't be doing disinfection tests and waste management tests in a BSL-4 facility. We need to have something that we can use in a BSL-2 facility that would be appropriate for whatever type of experiments we're doing. There's wastewater issues. How do you measure it in the wastewater? What is the fate of the organism as it goes from the point of generation down to the wastewater treatment facilities? As it goes through the sewer, you might have vector issues where the rats in the sewer might potentially pick something up. So, and the idea of getting mobile capacity in order to not have to transport these items in this complex packaging. If you can inactivate it on site, you can then go through a much less rigorous waste packaging and waste management process. Also, the potential for innovative treatment options would be nice, like microwaves. There's no data on those. And I have some resources. Thank you.